Hello and welcome to Better in Physics. Today I'm going to be talking about applications of Newton's laws. Specifically, I'm going to be talking about friction and fluid resistance. Let's jump right in. Friction is an intermolecular interaction where bonds form and break between two surfaces moving relative to each other. The smoother the surface, the more friction there will be, as it will be easier to form bonds between surfaces which are moving relative to one another. If enough bonds are formed, the surfaces can actually cold weld to each other, which is why things like engines, the piston within the engine must be lubricated, so there is a layer of fluid between the two surfaces so they don't cold weld. Between two surfaces, friction is typically proportional to the value of the normal force. In other words, the heavier the object, the greater the magnitude of friction. That is for the most part. And there are two types of friction: kinetic friction and static friction. Kinetic friction force is the force which is opposite to the applied force between two surfaces which are moving relative to each other. The vector, which is the addition of the normal force and the friction force, is known as the contact force. Now the friction force, that is the kinetic friction force, can be solved by multiplying the normal force by what we call coefficient of friction, in this case the coefficient of kinetic friction. While friction is not perfectly constant as two surfaces move relative to one another, we treat it as constant. And so the magnitude of our friction force is equal to mu sub k times n, or the coefficient of kinetic friction times the normal force. The other type of friction force is static friction force. And the static friction force can range between a value of 0, when there is no applied force, and some max value, which is mu sub k times n, or the coefficient of static friction times the normal force. Now, an object which is interacting with a surface will not move until the applied force overcomes the force of static friction, which is going to be opposite to the applied force. If we take a look at a graph, we'll see that when the box is at rest, the applied force will increase until it reaches a maximum friction force, which is the maximum static friction force. And once it overcomes that, it usually drops. In other words, it is easier to keep an object moving when there is friction than to start moving an object from an initial rest position. And as we can see here, like I mentioned previously, the kinetic friction force is not perfectly constant. However, again, we treat it as constant. The other type of resistant force is the fluid resistance. Fluid resistance is when an object is moving through a gas or a liquid. For example, as I move in my room, I'm moving through air, and the air exerts a force on me because I exert a force on it. For small objects moving at low speeds, we denote this fluid resistance as kV, where K is a constant proportional to the shape and size of the object and the properties of the fluid, and V, of course, is the velocity of the object. For fluid resistance for large objects at high speeds, we denote it by d times v squared, where d again is proportional to the shape and size of the object and also the properties of the fluid. Which means that actually when an object is falling through air or space, the force is not just equal to mg, but rather it is equal to mg minus kvy for the case of small objects moving at low speeds. Of course, we're using Newton's second law in order to find this relationship. Now, when mg minus kvy is equal to 0, then we can find the terminal velocity. You see, when mg minus kvy is equal to 0, then the object falling through air, for example, is now at equilibrium and is no longer accelerating. So the velocity has reached its maximum. And we can find this terminal velocity by adding over kVt and dividing it by k. And so our terminal velocity for small objects at low speeds is going to be equal to mg over k. Now, as a result from this relationship, we can actually find values of v of y, that is the velocity that the object is falling, in respect to t, along with the acceleration of the object in the y direction in respect to t, and also the position of the object in respect to t, using Newton's second law and then deriving it. So we start with the relationship ma sub y, or in other words, m dvy over dt, which means that the change in the velocity in the y direction over the change in time is equal to the acceleration, as we know, is equal to mg minus kvy. Well, if we divide both sides by k, we will get m over k dvy on the left, and of course I'm also multiplying by dt, and on the right I'm going to get v terminal minus vy dt. When we divide by k, we get mg over k, and we know that is equal to velocity terminal, and we get rid of this k. So we're left with v terminal minus vy. We pull a negative out, and then we put it on the other side, and then we multiply one side by mk, and the other side by vy minus vt. And then we'll have dvy over vy minus vt, which is equal to negative k over m dt. We integrate the left side over vy, and we integrate the right side over t. And what we're left with is a natural log of vt minus vy over vt, which is equal to negative k over mt. Now from here, we use an exponential to get rid of the natural log, and we're left with v of y is equal to v terminal times 1 minus e to the negative k over m times t. In order to find the acceleration in respect to time, we take a time derivative. Now v terminal is a constant value, so when we take the derivative, we're going to get a sub y is equal to 0 times 1 minus e to the power of negative k over mt, which is just going to go to 0, and then we're going to get v times k over m times e to the negative k over mt, and this I got using the product rule. Finally, since we know v terminal is equal to mg over k, when we multiply k over m, we're going to be left with just g. And so a sub y is equal to g times e to the power of negative k over mt. If we want to get the relationship of position in respect to time, then we integrate v of y in respect to dt over t. We're going to be left with two integrals, which is going to be vt dt and vt times e to the negative k over mt. Now again, vt is a constant, so we can pull that out, and we're left with one integral, which is dt integrating over t, which is just going to be equal to t, and then we're going to get the integral e to the negative k over mt dt integrating over t, and what we're going to end up with is vt times t minus m over k times 1 minus e to the power of negative k over mt. In any case, this has been the concept video for applications of Newton's laws. Hope to see you in the example video.